Here we go. Lesson 1-3 is about something called the definite integral, aka distance is a rectangle. I'm going to level with you. You've been letting yourself go. And so today we're going to get you back in shape. Let's imagine that we're going to go for a run. And you're going to move at a rate of 5 meters per second. And you're going to do that for 6 seconds. Question: how far did you run? Answer: well, the distance that we run is equal to the product of two things. The first thing is our velocity as time goes by, and the second is the change in time. So in the case of this problem, we can say 5 meters per second multiplied by 6 seconds is equal to, the seconds cancel and we get 30 meters. Now I challenge you to think about this graphically. Let's sketch a picture. So here's the time, here's the velocity as a function of time, and right now our velocity is constant. So at 1, 2, 3, 4, 5, I'm going to draw a horizontal line that runs for 6 seconds. So here's 0, here's 6 when we stop, and notice that we have a, ta-da, rectangle. And guess what? If we find the area of this rectangle, well, the height is always 5, and the base, which is incidentally equal to how much time goes by, is 6. So 5 times 6 is equal to 30. Translation: when we found 30 meters, we were really finding the area of this rectangle. Now, imagine that we go a step further. It's day 2. We're going to do some running, but this time you run for 6 seconds where your velocity is not constant, it's variable. And suppose that it's given by the equation 2 times the square root of t plus 1. All right. Well, we're still going to use the fact that distance is equal to the velocity over time times the change in time. The only problem is we don't really know what to plug in for velocity. And so what we're going to do is, again, try to think of this thing graphically. Here's time going by, here's the velocity, and I know that at time 0, if I plug 0 in here, we get a velocity of 1. And at time 1, if we plug 1 in here, we get a velocity of 3. And at time 4, I'm picking 4 just because this is a square rooting function. If we plug 4 in here, we get a velocity of 5. And so our graph is going to look something like this. Now, here's time 6. And just like in the last problem, where the area underneath our horizontal line gave the distance, the area under our curve is going to give us the distance because this is velocity multiplied by time. The thing is, since we don't know how to find the area of this, what I'm going to do instead is I'm going to break it up into little sections so that each section has a width of 1. And then what I'm going to do is I'm going to put a cap on each one of them. Now I'm putting the cap in a specific spot. I'm putting it here because if I put it here, I've missed a little bit of the area. See that? But I've also gained a little bit of area, and I'm going to say that those two are about the same. And let's say that the height at this moment is 2.2. Well, if I continue doing that, I will get a series of 6 different areas, and those areas should be able to approximate the distance. Okay, so I've gone ahead and I've estimated what the height of each one of these rectangles is. And I want to emphasize to you that making the width of each one of the rectangles equal to 1 second, that was my choice. And we could have made them smaller or larger. But the big idea is that now that we know this, I can say that the distance that I traveled on that first interval is equal to our estimate of 2.2 meters per second as the velocity times 1 second. And then I can just add up all the others. One thing that I'd like to emphasize to you is that this is not an exact science. And so one of the things that can be kind of frustrating is that if you were to do this problem entirely on your own, you would probably come up with slightly different numbers for these heights, which means that you would have a slightly different sum. When I sum all of these up, I get 25.6 meters. And so the moral of the story is that it's okay that we're not all getting the exact same answer. All right, so now let's generalize this. I want to give you a definition for something called the definite integral. And it would be helpful if first we were to look at a picture. So imagine that you've got a starting time, let's call that starting time A, and an ending time, let's call that ending time B. And then you've got this function, and this function is not sitting still. It's going up and it's going down, and maybe it's even going back up. The definite integral is a way of calculating a product, and that product is going to be the product of f of x and the change from A to B. Now the change from A to B is given by B minus A. So when we say that the definite integral So now I got cut off and I skipped ahead a little bit. So here's your definition of the definite integral. It's the product of f of x and b minus a. And so the product would be this height times this base, and the product ends up being this area right here. Now the beauty of the definite integral is it's designed for dealing with situations where the height keeps changing. You know, it's here, and then it's up to there, and then it's all the way down to here, and then it's back up. Okay, so there's the definite integral. I want to show you the notation. I'm getting an elongated s, and that s stands for sum. You may recall that in the last problem, we added up a bunch of rectangles. So what we were really doing is summing them. And we sum them from the start point, which is right here, to the end point, which is right here. And it's the sum of a product. That product is f of x and the change in x, which we're going to call dx. Okay, so again, this means sum. This is your start. This is your end. This is the height of the rectangle. And this right here is the width.